Hello, and welcome to our discussion of pointwise convergence of Fourier series. Let's start with an integrable function f from the interval minus p to p into the complex numbers. The integrability of f, of course, means that its Fourier coefficients f hat of k are all defined. Here's our question. For what, if any, points x in the interval minus p to p does the Fourier series of f at x converge? This is to say, when does the limit as n goes to infinity of the sum from k equals minus n to n of f hat of k times e to the ik pi x over p exist? And in particular, when does the limit equal f of x, or maybe something to do with f? So to answer this question, we need a new, or depending on how you talked about things in calculus, possibly old concept, the notion of piecewise continuity and differentiability of functions. Because we're going to make precise some continuity and differentiability conditions on our function f that guarantees both that the Fourier series converges, that this limit as n goes to infinity exists, and that the limit either equals f of x or equals something pretty close to f of x. So it tells us not only existence of the limit, but also the value of the limit. Let's start with a picture. Here I've drawn in blue a function f on the interval 0 to 3. You can see f starts at the value 0 at 0, it goes up to the value 2 at x equals 1, then down to the value 1 from 2 to 3. And this is clearly a continuous function because I have a blue unbroken curve here on the screen, and we can also bet that it's not going to be differentiable everywhere on the interval 0 to 3 because I have corners at 1 and at 2. And indeed, if I were to graph the derivative of f, I would see that it was constant from 0 to 1, and then it jumps down to a different value between 1 and 2, and then it jumps to another value between 2 and 3. In particular, the value between 2 and 3 is just 0 for the derivative because there it's a horizontal line. And when I'm graphing things along the x-axis, I like to shade them in a little bit so you can see better against the black of the x-axis. So in words, what do we observe about f? F is continuous on 0 to 3, the graph is unbroken. F is differentiable on 0 to 3, except at the points x equals 1 and 2, because I have corners there. And this derivative f prime is continuous on the interval closed from 0 to open at 1, on the interval open at 1 to open at 2, and on the interval open at 2 to closed at 3. So I have some jump discontinuities in f prime here. And I also note a little more subtle aspect. F and f prime have left and right limits at all points. So you pick a number between 0 and 3. F is defined at any one of those numbers, and the limit from the left to that point x equals the limit to the right from that point x of f. That's obvious because f is continuous. F prime is discontinuous, it has jump discontinuities at 1 and at 2, so its limits don't exist at 1 and at 2, but the left and right limits totally do. Like if you approach x equals 1, the left limit of f prime, well, it stays up at 2, so that limit is 2, and the right limit of f prime is minus 1. So left and right limits exist at all points. There's no blow up, there are no asymptotes or things going to plus or minus infinity in either of these graphs. They're pretty well behaved, they're pretty tame graphs. Here's another picture. So I'm going to start on the left with the function f of x, and on the right I have its derivative f prime of x. I should have a prime at the top, sorry. So let's look at f of x. F is now discontinuous. So I go at the value minus 2 in the interval minus 2 to minus 1, and then I shoot up to a not exactly horizontal line, looks like f of x equals x between minus 1 and 1, and then I shoot up to another constant on the interval 1 to 2. And so f has some jump discontinuities at minus 1 and at positive 1. So f is discontinuous at minus 1, 1. Certainly f won't be differentiable at minus 1, 1. And if I go over to my graph of f prime on the right, again I should have written an f prime on the y-axis there, I see that between minus 2 and minus 1, I have constant 0 slope. between minus 1 and 1, I have constant slope 1, and between 1 and 2, I have again constant slope 0. So this looks very similar to what I had on the previous slide, except that now my function f is discontinuous from the start, so certainly the graph of f prime is discontinuous. What do I see? F is continuous on minus 2 to 2, except at minus 1 to 1 and 1, we knew that. F is differentiable on all of minus 2 to 2, except at x equals plus or minus 1. And f prime is continuous on 3 intervals, minus 2 to minus 1, minus 1 to 1, and 1 to 2. And again, f and f prime have left and right limits at all points in this interval minus 2 to 2. So even though the full limit doesn't exist, for example, the limit as x goes to minus 1 of f on the left, well, that's going to be minus 2, because I'm down at minus 2 on the left of minus 1. But on the right of minus 1, I'm sort of on the line f of x equals x, so that limit would become minus 1. So I have discontinuities, but the left and right limits exist, and that's true for both f and f prime. I don't have, again, any asymptotes. I don't have things blowing up to plus or minus infinity. I would call these functions very tame. So let's give these functions a name. I'm going to let C1 piecewise of the interval a to b be the space of all functions f from the interval a to b into the complex plane such that the following hold. F is continuous and differentiable at all but finitely many points of the interval a to b. If I put f of x plus is the limit as t goes to x from the right of f of t, and f of x minus is the limit as t goes to x from the left of f of t, these two limits exist for all x in the interval a to b. Of course, I would only have a right limit at the left endpoint x equals a, and I would only have a left limit at the right limit, or the right endpoint x equals b of the interval, but we don't worry too much about that. And I also have left and right derivatives existing for all x in the interval a to b. So if I take my classical difference quotient, f of x plus h minus f of x over h, and I send h to 0 from the left or to the right, these derivatives limits also exist regardless of what x is, and they're equal for all but finitely many x. So this is saying that f can fail to be continuous or differentiable at some finitely many points, but f will always have left and right-hand limits regardless of where I am on the interval. And the same, even though the derivative doesn't have to exist at any points, these left and right derivatives, these left and right limits of the difference quotient, all exist. So armed with this new kind of function space, this very precise notion of piecewise continuity and differentiability, I can state a result on the convergence of Fourier series. So let's take a function f that is in C1 piecewise of the interval minus p to p. Then I have the marvelous convergence result for the Fourier series of f at x. First of all, if x is strictly between minus p and p, so x is not the left endpoint and it's not the right endpoint, then the Fourier series for f at x is equal to f of x plus f of x minus over 2. So that means all I have to do to figure out what the Fourier series sums to is calculate the left and right limits of f at this point x. And because f is in the space C1 piecewise of minus p to p, these left and right limits, f of x plus and f of x minus, will always exist for f, or rather for that value of x, although the left and right limits don't have to be the same. And then something slightly different happens when you are at x equals plus or minus p. The Fourier series for f at x equals plus or minus p at the endpoints is f of the right limit for minus p plus f of the left limit for positive p over 2. In particular, if f is continuous at a point in the interior of this interval minus p to p, not including plus or minus p, then the left and right limits for f at that point x have to be the same, and so the Fourier series for f at x converges right back to f of x. So continuity on the interior of the interval guarantees not only convergence of the Fourier series at x as a series of complex numbers, but convergence back to your original function f of x. And then if f is continuous at x equals plus or minus p at the endpoints, and if you have f of p equals f of minus p, then you'll have the Fourier series for f at plus or minus p equals f of plus or minus p. We'll talk about that a little bit more in the next section. The issue here being at the endpoints of the interval that you have to have 2p periodicity for the Fourier series to converge. So the endpoints of the interval are a little bit weirder, but that's not surprising because the Fourier series is composed of 2p periodic functions, so it should sum back to a 2p periodic function. So this is a very nice result for C1 piecewise functions. It is very much worth memorizing and being able to quote verbatim on exams and on homework. And later on, next week, we'll also talk about how this result is a little restrictive. After all, our Fourier series, we can define them for any integrable function, just have to get those Fourier coefficients to exist. But for the Fourier series to converge according to this theorem, we have to have some pretty harsh continuity and differentiability requirements. We can't have asymptotes, we can't have infinitely many discontinuities, we have to have very good behavior of the function. For now, let's study a very simple function and evaluate its Fourier series without actually calculating any of the Fourier coefficients. So I'll put f of x to be 0 for x between minus 1 and 0, and 1 for x between 0 and 1. And our job is to find a formula for the Fourier series of f on minus 1 to 1. And often in the homework or on a test, I'll say, do this without calculating any integrals or calculating any Fourier coefficients. This means I want you to use the Fourier convergence theorem. So we look at f. It is continuous on minus 1 to 1 except at x equals 0. So that tells us that the Fourier series for f at 0 should be f of 0 plus f of 0 minus over 2. So that's my limit from the right of f at 0 and my limit from the left at 0. So my limit from the right at 0, well, f is taking value 1, so that's 1. And my limit from the left at 0, going to 0 from the left, f is 0. So I get 1 plus 0 over 2, which is 1/2. So the Fourier series for f at 0 is equal to 1/2, which is definitely not f of 0, but that's not surprising because f is not continuous at x equals 0. On the other hand, f is continuous on the open interval minus 1 to 0. So for x strictly between minus 1 and 0, we should have the Fourier series for f at x is f of x plus f of x minus over 2. F is continuous at this x, so the limit from the right is equal to the limit from the left. Both those limits are equal to 0. So my Fourier series for f at x is 0 plus 0 over 2, which is 0. And that is what f is equal to for x strictly between minus 1 and 0. Again, not surprising because f is continuous there. And last, f is continuous on the interval 0 to 1, open at both 0 and 1. So for x strictly between 0 and 1, I should get the Fourier series for f at x to be, say it again with me, f of x plus f of x minus over 2. And there my limit from the right and the left are both the same. They're both equal to 1, so that's 1 plus 1 over 2. That's equal to 1. So I did everything in the interior of the interval minus 1 to 1. I had my discontinuity point at x equals 0, and everything else was nice and continuous. And then at the endpoints, I have my special case. The Fourier series for f at plus or minus 1 is the limit from the right as x approaches minus 1 of f, plus the limit from the left as x approaches positive 1 of f. And chase through that and make sure you're reading it aloud with me and you understand what that means. Okay. So what's the limit from the right as I approach minus 1? Well, as I go to the right of minus 1, that is for x bigger than minus 1, f is 0, so I get a 0 here. And if I approach positive 1 from the left, when x is less than 1, f has the value 1, so I get a plus 1 there. So my Fourier series for f at plus or minus 1 is 0 plus 1 over 2, and that is 1/2. And that is certainly not the value that f has at either +1 or -1, but that's not surprising because f is not periodic, right? F is 0 on one half and 1 on the other half. So I shouldn't expect the Fourier series of f to converge back to f at plus or minus 1. So altogether, I conclude that the Fourier series for f at x is 1/2 for x equals -1, 0 for x strictly between -1 and 0, 1/2 again for x equals 0, 1 for x strictly between 0 and 1, and 1/2 again for x equals 1. And this is usually how I like to write solutions to these problems when I'm trying to figure out what does a Fourier series converge to. I'll write it as a piecewise formula starting with the left endpoint, x equals -1, and then going piecewise through the interval as I need to until I hit the right endpoint.